Welcome to EPG Pathshala, lectures on numerical methods. Earlier modules we have seen the various techniques for interpolation, piecewise interpolation and inverse interpolation. Now the next two modules we will be talking about curve fitting. Curve fitting is also a technique for approximating a function, just as in the case of interpolation, but here our emphasis is slightly different than that of interpolation. The success of interpolation technique in predicting true relationship y is equal to fx between the process variables x and y is mainly based on the assumption that the given data points xi, yi, I equal to 1 to 3 up to n are exact. We are almost certain that the observations made on the variables x and y are error free, and hence we are looking for a function fx which passes through the given data points that predicts a relationship between x and y. However, most of the experimental observations are not so precise due to limitations of measuring instruments and or the observer. Hence, in most of the real life processes, the observations have certain random measurement noise, and therefore interpolation may not give good estimate of the true relationship. To see this, we consider an illustration. Consider a rectangular water tank having square base with area 1 square meter and the height of 2 meters, in which initial water level is 1.6 meters. The water flows out of this tank from a tap at the bottom at the fixed rate of 0.15 cubic meters per minute. Sensor is installed in the tank to measure the level of the water at an interval of 2 minutes, and 5 observations are taken. The measuring accuracy of the sensor is 90%, and hence observed data is not as accurate as theoretical values. Theoretically you can see that the process here says that initial water level is 1.6 meter and it is flowing out at the rate of 0.15 cubic meter per second, and cross sectional area is equal to 1, and therefore we can say that the water level decreases or height of the water level ht can be considered as 1.6 meter initial minus 0.15 into t. So we have got theoretically relationship between the time and the height as a linear relationship. Now, because the measuring accuracy of the sensor is 90% and hence observed data is not as accurate as theoretical values. So therefore what happens is, if you look at the theoretical estimate can be given by ht equal to 1.6 minus 0.15 t. The reason being that your cross sectional area is 1, so height will determine the cubic meter water volume in the tank, and this water volume decreases at the rate of 0.15 per minute, and therefore we can say that height ht will decrease at the rate 1.6 minus 0.15 t. So this is the exact relationship between the time and the height of the water level. Now, because of measurement inaccuracy, the water level observed are slightly different than the theoretically estimated water levels. So you can see that here at time ti, that is 0, 2 minutes, 4 minutes, 6 minutes and 8 minutes, the observations are made at these 5 points. So theoretical water level will be 1.6, 1.3, 1, 0.7 and 0.4, because every 2 hours 0.3 cubic meter will be reduced. And water level observed is somewhere around 1.48, 1.33, 0.923, 0.735, 0.43. So in the interpolating polynomial from the observed data, so now if you look at the observed data, that is the first row and the third row, so 0 and 1.48, these are the nodes that we are going to consider: 0, 1.48, 2, 1.33, 4.923, 6.735 and 8.43. The interpolating polynomial, if you compute from this, then we get it as 4th degree interpolating polynomial P4t is equal to 1.48 minus 0.075 t minus 0.0321 t into t minus 2 plus 0.01 t into t minus 2 into t minus 4 minus 0.002 into t minus 2 into t minus 4 into t minus 6. You can see that this is Newton's divided difference kind of approximation, or Newton's forward difference interpolating polynomial form we are using here, and we are not giving the details of how the differences are calculated, and it has been the routine exercise in the previous modules. So this is your 4th degree polynomial, interpolating polynomial, giving the relationship between the height and the time, that is P4t gives the estimated height in that. If instead of using interpolating polynomial of degree 4, if we use piecewise linear polynomial interpolation, then your P1t will be given by 1.48 minus 0.075 t for the time between 0 and 2, 1.33 minus 0.2035 t into t minus 2 for time between 2 and 4, 0.923 minus 0.94 into t minus 4 between 4 and 6, and then 0.735 minus 0.1525 into t minus 6 for time between 6 and 8. So we have got 2 experimental estimates for the height and 1 theoretical estimate, as already said, that is ht equal to 1.6 minus 0.15 t. The figure 1 shows the comparison of the plots of these 3 functions, which clearly indicates that interpolation or piecewise interpolation technique does not give satisfactory estimate of the true relationship. You can see here that true relationship is represented by a straight line, that is original curve, and then piecewise linear interpolation is given in terms of red, and the 4th degree polynomial interpolation is given in blue. And you can see that these 3 curves do not match with each other, and therefore the experimental estimates are not as close as to the theoretical estimate. So in the above illustration, initial water level and the outflow rate was given, and it was easy to determine the true relationship between water level h and the time t, and therefore comparison was feasible. But imagine a situation where the same water tank system is considered, but neither the initial water level h0 nor the outflow rate r is given. Instead, the observed data TI/HI for I equal to 1 to 5 is given. Then in this case, we only know the trend of the data, and that is linear, because you can see that if you draw those points, there's some almost lying on a line, straight line, and that straight line will be of the form ht is equal to h0 minus r into t, where r will be the flow rate and h0 is the initial height, and both of them are unknown to us. So here h0 and r are required to be estimated from the observed data, so that the estimated values and the observed values of the water levels are as close as possible to each other. Note that the estimated linear relationship must be valid in the entire domain of observation, and that such a line need not pass through the observed data points, as we no longer rely 100% on the observed data points. So therefore, we don't want that line to pass through the observed data points. Also note that since the line represented by 1 is not restricted to pass through any of the data points, there could be infinitely many choices for choosing such a line. So we are required to determine a unique line which best fits the observed data, means which is giving us the most close estimates, or estimates which are very close to the observed data. In general, consider any process involving an independent variable x and a dependent variable y, and suppose that n data points xi, yi, I equal to 1 to 3 up to n are given, and one has some idea about the trend of the data, and hence can predict the form of the relationship between x and y. The technique by which the unique relationship in the predicted form is determined so as to best fit the observed data is called curve fitting. So suppose that n data points xi, yi, I equal to 1 to 3 up to n are given, and one has some idea about the trend of the data, and suppose that the predicted form of the relationship between x and y is given by y equal to f of x comma a0, a1, a2, a3, ak, which are the parameters, where a0, a1, a2, a3, ak are the parameters determining the form of the function f. To determine the specific relationship, the values of the parameters are determined so that the estimated value of y at x equal to xi, that is fxi, and the observed values yi's are close to each other. The closeness of these values is measured in terms of total square error as a function of the parameters given by error in terms of A0 when parameter values are A0, A1, A2, A3, An is equal to yi, that is observed value of y, ith observed value of y, minus fxi, that is predicted value of y at x equal to xi. And you take the square of this error in order to make sure that negative positive effects are eliminated, and you sum it over all the observations 1 to n. So what we are trying to do is the closeness of these values is measured in terms of the total square error. So naturally, to determine the specific relationship, we find A0, A1, A2, A3, An which minimizes this total square error. The technique of determining fx that minimizes this total square error is called as a least square curve fitting technique. Usually, we fit certain standard curves as mentioned in the table 1 below to the data for many of the real world processes. So relationship, suppose that predicted relationship or trend is linear, then we fit a curve fx equal to a0 plus a1x, and parameters here are a0 and a1. If the predicted relationship is quadratic, then the curve that we fit is fx equal to a0 plus a1x plus a0 a2x square, and a0 a1 a2 are the parameters. In general, if it is a polynomial of degree m, then fx is equal to a0 plus a1x up to am x raised to m, and parameters are a0, a1, a2, a3, am. Power function, if you write, so fx equal to a into x raised to b, where a comma b are the parameters. Exponential function, if you write, then fx equal to a e raised to bx, a comma b. Logarithmic function, which is natural logarithm we are considering, so fx equal to ln of a dot x plus b, and a and b are again the parameters. So these are the usual curves that we try to fit to the given data. You may also fit any arbitrary data, but for that you might need some more sophisticated techniques. The first three of these are polynomial functions, whereas the other three are not polynomial functions or non-polynomial or non-linear functions. So in the first module, we are going to discuss the polynomial curve fitting. So again, consider the data points xi, yi, and I equal to 1 to 3 up to n are given. We would like to fit a straight line fx equal to a0 plus a1x to this data. So we are talking about fitting a first degree polynomial or a linear function. For that, we have to find the values of a0, a1 which will minimize the total square error, which is given by e of a0 comma a1, which is equal to I equal to 1 to n yi minus a0 minus a1 into xi whole square. By a known result from calculus, the necessary condition for error function e a0 a1 to be minimum at a0 a1 is that at this points partial derivatives with respect to a0 and a1 must be 0. Now if you take partial derivatives with respect to a0, I will get the equation like this: I equal to 1 to n 2 into yi minus a0 minus a1 into xi into minus 1, because coefficient of a0 is minus 1 here, and that will give me, and second partial derivative with respect to a1 will give me I equal to 1 to 3 up to n 2 into yi minus a0 minus a1 into xi into minus xi, as the coefficient of a1 is minus xi, and I am equating both these partial derivatives to 0. That will give me two conditions on a0 and a1. If you simplify this, we can get the conditions like this. So sigma I equal to 1 to 3 up to n yi minus, since we are adding this n times, we will get n into a0 minus a1 into sigma xi I equal to 1 to n xi equal to 0. This is what we will be getting. And the second equation I will be getting is I equal to 1 to n yi xi minus a0 into I equal to 1 to n xi minus a1 into I equal to 1 to n xi square. This is what I will get. So these two equations I am getting. You can see that sigma summation I equal to 1 to n yi is known because all yi's are known. Summation xi I equal to 1 to n are known because all xi's are also known. So similarly, sigma xi yi also is known, sigma xi square is also known, and therefore these are the two simple equations in a0 and a1. Solving this 2 by 2 system of equations of unknowns, a0 equations in unknowns a0 and a1, we get a0 equal to sigma I equal to 1 to n xi square into sigma I equal to 1 to n yi minus sigma I equal to 1 to n xi yi, sigma I equal to 1 to n xi upon n into sigma xi square I equal to 1 to n minus sigma xi whole square. And A1 is given by n into sigma I equal to 1 to 3 up to n xi yi minus I equal to 1 to n xi into sigma yi I equal to 1 to n, and n into sigma I equal to 1 to n sigma xi square minus sigma I equal to 1 to n xi whole square. So that means we can get a very concise formula for A0 and A1. So the best fitted line to the given data in that case is given by f(x) equal to A0 plus A1x, which is also called a regression line of y over x, or least square line or regression line of y over x. Now let us look at the illustration 1 and come back to the illustration 1. We know that we are given observed data values of water level and the time. So time is 0, 2, 4, 6, 8, and corresponding observed water level are 1.48, 1.33, 0.923, 0.735 and 0.43. Fit a line ft equal to h0 plus rt. To this data we use formula 2 to determine h0 and r. To compute the summations involved in the formula 2, we use the following table. So we have got Ti equal to 0, 2, 4, 6, 8, that is first column, and summation Ti. Instead of x I will be using here Ti because that is independent variable I am using, and instead of yi I am going to use hi because hi becomes the dependent variable. So if I substitute these values in the parameter, I have to use sigma Ti and sigma hi kind of thing. So first sigma Ti is given by 20, then hi, if you add all of them in the second column I get sum hi. So that is sum h, I am denoting it by sum h. This is sum t, first is sum t, the second is sum h, then sum t square. So Ti square I am taking the square of that. So 0 square is 0, 2 square is 4, 4 square is 16, like that, and you add up and that gives me 120, and then you take hi into Ti. So hi into Ti, so product of the first two columns and then you sum over that column, that will give me sum th. So first sum is sum t, second column gives me sum h, third column gives me sum t square, and fourth column gives me sum th. Now putting these values in the formula, I get h0 in that format. So 120 into 4.898 minus 14.202 into 20 divided by 5 into 120 minus 400, and on simplification I will get 1.5186. Similarly r I will get it as 5 into 14.202 minus 20 into 4.898 and 5 into 120 minus 400 in the denominator. So that gives me minus 0.13475. Hence the equation of the least square line, I get it as ht equal to 1.5186 minus 0.13475 t. Now if you compute the water levels estimated and water level estimated by theoretical relationship, and we already have the observed water level, and compare all of them together, then we can find out how much error we are getting in each of these cases. So the first row here in the next table, you get first row gives me the time values Ti, the second row gives me water level observed and they are as mentioned earlier, then water level estimated, which is obtained using the relationship which we already predicted, and that relationship gives me water level at 0 is 1.5186, at 2 1.2491, at 4 0.9796, at 6 0.7101, and at 8 0.4406. Now if you take the difference between observed water level and estimated water level, I get and square these values, then I will get error for each individual observation, and summing that over all the elements in that row, in the fourth row, I will get a total square error between observed and estimated values. Just for the sake of interest, we may also find out now the different error in the actual theoretical relationship and estimated relationship. So that I am trying to get it from here. So I am writing theoretical estimates as 1.6, 1.31 as predicted earlier, and then I am taking the difference with the elements in the third row. Then I will get the estimate HIO observed minus HIT, that is theoretical heights, and square each individual observation, and then I will add up, and all this adding up will give me the error. So minimum total square error between the observed and estimated values is 0.008, whereas total error total square error we can say, between theoretical and estimated values is 0.0233. The figure 2 shows the scattered plot of the given data points and the estimated line fitted this data, which minimizes the least square error. Also, comparison of this estimated least square line and the theoretical linear relationship determined in illustration 1 is depicted in the figure 2b. So, you have got these figures which gives me this. So, you can see that observed data line is not passing through any of the data points, but it is very close to the data points. And then this is the black is the theoretical line, whereas observed line. So, observed data line need not be same as the theoretical estimate. But one can see that estimated values are more close to the observed data points rather than theoretical data points, because that is how we have obtained those estimates. Note that the estimated least square line is more close to the observed data than the theoretically determined line. This is because the principle of least square curve fitting, which states that among all the curves in the predicted form, the least square curve is closest to the given data points with respect to the total square error. The closeness of the predicted functional relationship y equal to fx x0 a1 a2 a3 ak with observed data points can also be measured in terms of other types of errors. And total absolute error, for example, we take, so E1 equal to A1 A2 A3 AK or A0 A1 A2 A3 AK, I equal to 1 to k of absolute value of yi minus estimated value of yi. So, f of xi and A1 A2 A3 AK. So, and you sum over all the observations. Maximum error you consider it as FE2 A1 A2 A3 AK, which is the maximum of all these error values. Now, since these two error functions are not differentiable, the technique used on the basis of partial derivatives cannot be used to minimize these errors, and hence total square error is used in the curve fitting, and hence in this the technique is called as least square curve fitting. See, the closed form solutions that we have got for the parameter values is because we are using those partial derivatives and their equations dependent on equating this partial derivatives equal to 0, which may not be possible if we use the other two forms of the errors here. Fitting a polynomial of degree m greater than 1 is also again similar. So, given data points xi y I equal to 1 to n, it is required to fit a polynomial px of degree less than m, less than or equal to m. Note that if n is equal to m, the best polynomial fitting the given data would be the interpolating polynomial. As in that case, the corresponding total error will be 0, because pxi will be equal to yi in the interpolating polynomial. Hence, we always consider m less than or equal to 2, very small as compared to n. And the polynomial px has the form px equal to a0 plus a1x plus am x raised to m, we write down there, and hence total square error is given by e a0 a1 a2 a3 m I equal to 1 to 3 up to n yi minus a0 minus a1x and so on am xi raised to m and whole square, which is to be minimized. So, by a necessary condition, the values of a0 a1 a2 a3 which minimizes this must satisfy partial derivative of e with respect to aj must be equal to 0 for all j equal to 0 to 1 to n. And if you take these partial derivatives, you can see that partial derivative of e with respect to aj will be given by t equal to I equal to 0 to n 2 times yi minus a0 minus ai xi minus up to am xi raised to m into bracket minus xi raised to j, because that is the coefficient of aj in that expression. These conditions gives rise to the following system of equations. If you write for j equal to 0, 1 and j equal to 1, 2, 3, 4 so on, so 0, 1, 2, 3 up to n, then I will get m plus 1 equations in m plus 1 unknowns, and these m plus 1 equations are given here, which I will not read through, but thus to obtain the desired values of a0, a1, a2, a3, one must solve this m plus 1 by m plus 1 linear system of equations 3. These equations are usually called normal equations. Fitting a polynomial of degree m greater than 1, so note that the coefficient matrix of the system of equations 3 is real symmetric, and one can prove that this matrix is non-singular if n is greater than m, and if the observed x values x0, x1, x2, xn, xn are distinct. Hence, under these assumptions, the system 3 has an unique solution, which means that the least square polynomial that minimizes the total square error is unique. So what we are saying here is that coefficient matrix of the system of equation 3 is real symmetric, and one can prove that this matrix is non-singular if n is greater than m and if the observed x values are distinct. And in that case this system will have unique solution, and therefore the unique polynomial that is to be fitted can be obtained by solving this system of equations. Why it is symmetric? Because you can see that the diagonal elements are fine, but upper diagonal and lower diagonal elements, they match with each other. That means Aij matches with Aj, and therefore this matrix is symmetric. So what we are now doing is, in general, it is not easy to solve such a system of equations for a large value of m, and hence concise formula for the coefficients a0, a1, a2, a3, m are not derived as in the case of a linear fit. However, because of the symmetric nature of the coefficient matrix, efficient numerical methods are available for solving such a system. These methods will be discussed in the later modules. This is example 2, which gives me fit a quadratic polynomial is a0 plus a1x plus a2x square to the following data. Again we are taking the values x as 1.0, 1.5, 2.0 up to 4.0. They are equally spaced values here. Y equal to 1.1, 1.2, 1.5, 2.6, 2.8, 3.3 and 4.1. For this purpose we have to solve the system of linear equations 3 taking m equal to 2. So we evaluate the summations involved in the above system in the following table. So we are finding out those values. So we have got xi yi in the first two columns, xi square, xi cube, xi raised to 4, xi yi and xi square into yi. Now these are the sums that we need, and we are finding out these values by taking square of the first column as xi square, cube of the first column, or multiplying xi by the third column we are getting xi cube. Similarly we get xi4, xi into yi, that is first two column, product of first two columns are given in the last but one column, and xi square into yi is given in the last column. And if you add up all of them, we will get sum x equal to 17.5, sum y equal to 16.6, sum x square equal to this, sum x cube, and all those sums are given to you. And if we use that, we will get a system of equations, 3 by 3 system of equations like this, if you write that in the equations forms given in 3. So the solution of this system is obtained using MATLAB command solve, because we have not studied the methods for solving such systems so far. We will be using ready-made MATLAB program for that, and that gives me value of a0, a1, a2 as a0 as 0.4571, a1 as 0.3929 and a2 as 0.1286. And if you compare the observed values, and this is the predicted polynomial. So px equal to 0.4571 plus 0.3929x plus 0.1286x square, and then xi we are given, then observed values we are given already, estimated values we are computing from this relationship, and then error we are computing, and you can see that the minimum total square error is given to be 0.2385. So the figure 3 shows the scatter plot of the given data points and the estimated quadratic polynomial fitting this data, which minimizes the local square errors. We can see here that the quadratic polynomial is moving, and these are the scatter plots. So most of the points are close to the estimated curve. If you consider the algorithm line fit to fit the straight line a plus bx to the given data points, we can think of, and that gives me input as a number of data points n, data points xi yi for I equal to 0, 1, 2, 3 up to n. Iterative step is to compute these sums, actually sx, sy, sxx, sxy. So we are initializing all these sums to 0, and then we are trying to find out for I equal to 0 to n, sx equal to sx plus xi, sy equal to sy plus yi, sxx equal to sxx plus xi square, and sxy equal to sxy xi plus yi. So that is a very simple for loop which computes all these sums, and after computing all these sums we are putting it in the formula A for A and B. So A equal to sxx star sy minus sxy star sx divided by n into ssx minus sx square. B equal to n star sxy minus sx star sy divided by n star sx minus this. So this is what we find out, and compute total square error E equal to 0 by estimating these values, and you finding out estimated values of yi, and e is equal to e plus yi minus y estimated I, and whole square we are taking. So output will be coefficient AB and least square error. So this line fit algorithm will give you how to fit a line to the given data. The time complexity is also very easy to compute in this case. Algorithm obtained in terms of the number of arithmetic operations performed for implementing the algorithm. So A is the time required for addition, subtraction, M is the time required for multiplication and division, and the time complexity is measured in terms of A and M, and thus the time required for line fit algorithm, time for execution of the first for loop plus time required for evaluating coefficients A and B, and plus time required for execution of the second for loop. So first for loop is done n plus 1 times. There 4 additions and 2 multiplications are involved. So therefore first term will be 4a plus 2m into n plus 1. Then second we need 4 addition operations and 10 multiplication operations for evaluating a and b, and the last for loop takes 3a plus 2m into n plus 1 values, and that is how we get the total time complexity as 7a plus 4m into n plus 11a plus 14m. Thus, the asymptotic time complexity for this particular algorithm is order n. Algorithm polyfit will be similarly taking will depend on the how much time the MATLAB program takes for computing solving that system of linear equations, and normally we take input again as n and the data points xi, yi, and then we compute this iterative step. We evaluate this m plus 1 square sums Sij for I equal to 0, 1, 2, 3 up to m, j equal to 0, 1, 2, 3 up to m, and Sij is equal to k equal to 0 to n x k I plus j, and m right hand side sums will be bi equal to x k raised to I y k, k equal to 0 to n. Now compute from 0 up to 2m powers of each xk, because these powers are required once and for all and every time, and then you need not evaluate them separately, and we are calculating these powers of xk as zkp and storing them in 2-dimensional array like this, zkp, which is equal to xk raised to p. So for k equal to 0 to n, zk0 will be equal to 1 and p equal to 1 to 2m, zkp will be equal to zk p minus 1 star xk, and this is how we can get all the powers of x raised to k. Now compute m plus 1 cross m plus 1 coefficient matrix S and the right hand side m plus 1 dimensional vector B. These are the two things that we want to calculate. So since S is symmetric, we compute only lower triangular part of S and including diagonal, and upper triangular part will be simply the mirror image of the lower triangular part. So for I equal to 0 to m, we get bi equal to 0. So first we are calculating right hand side vector. So bi equal to 0, and then for k equal to 0 to m, we are adding bi equal to bi plus zki. Zk is xk raised to I into yk, and that sum we are calculating. So all the right hand side components of right hand side vector are calculated like that, and then we are calculating those sums. So for j equal to 0 to I, this is also included in that for loop, initial for loop here, for I equal to 0 to m, and now we are taking for j equal to 0 to I, we are getting Sij, because we are taking only lower triangular part. So Sij equal to 0, and for k equal to 0 to n, we will get Sij equal to Sij plus zk I plus j. So that is how we get those summations also. Store elements in the upper triangular part. So we are taking Sij as the mirror image of Sji, but we are taking I equal to 0 to m minus 1 and j equal to I plus 1 to m. So we are taking upper triangular part here. So solve the system Sa equal to b by calling a MATLAB routine or command solve. This gives you coefficients of the least square matrix A0, A1, A2, A3, N, which computes total square error. Then we compute the total square error. So first compute estimated values of y in the array y e k, and k equal to 0 to n. We take for k equal to 0 to n, y e k equal to initialize it by a0, and then you go on adding term by term there. So that is equal to for j equal to 1 to m, y e k equal to y e k plus a k star z k j. Z k j is x k raised to j. So that is how we go on adding, and we get y e k. Then compute error capital E equal to 0, and for k equal to 0 to n, we are considering E equal to E plus that difference between the observed and the estimated values square. We go on adding term by term, and then we get the output as the coefficients a0, a1, a2, a3, n, and the total square error E. The time complexity of the polyfit algorithm will depend on time required for the MATLAB routine used in the algorithm. However, the time required for the rest of the computation in the algorithm is computed in terms of A and M as in the earlier modules. The time complexity of algorithm polyfit will be equal to time required for computing array ZKP, time required for computing matrix S and vector B, time required for computing array YEK and error E, and time required for MATLAB routine. So, there are 4 components here, 4 terms here. The first term will be easy. I am cutting short the details of these computations here because most of the things we have been doing so far in the various modules. So, you can easily compute these sums and the multiplications required here. So, a by 2 into m square plus 4m plus 7 by 2 into a into m. Small m is the degree of the polynomial and capital M is the time required for multiplication of one multiplication operation. 4a plus 2m into n plus 1 and time required for MATLAB routine. So, to summarize the things that we covered in this module, we can see that we are talking about curve fitting techniques here. In the initial part we said that why curve fitting is required. Then we have said that what kind of curves we can fit to the observed data, and we have seen about 6 different curves which can be fitted, out of which polynomial curve fitting was discussed in this particular module. We talked about the line fit, in which case we have got the coefficients in a very concise form, and we have also discussed the line fit algorithm in full details and its time complexity was calculated. Similarly, higher degree polynomials also can be fitted, and illustrations of that is given. Also, the algorithm for polyfit algorithm is also discussed here in this case, and because we have not studied the techniques for solving the systems of linear equations, we are using here ready-made MATLAB program for solving such system, and therefore, the time complexity subject to the addition of this MATLAB time required for MATLAB program has been also calculated for polyfit algorithm in this module. Thank you.